Welcome back to ECE 441A, 541A. I have to be somewhere other than in my office this afternoon, so I won't be in office hours today, but normal office hours after that in terms of this week. I just this morning posted another set of notes and video. It's 10-minute video. It's not that long for the velocity gain constant. If we went over that or didn't go over that enough in the last time that we were together when we were discussing setting the gain in our phase lag Bode Plot controller design, maybe that will help you understand that process as far as how do we go about selecting the gain constant. Homework 8 is due tomorrow. The lab number 3 is due a week from today. A lot of things are due a week from today, actually. 2 new homework sets, which are now available on D2L, and teacher course evaluations. If you haven't yet done that, that is useful for me to get feedback from you as to how I can change the class. It's obviously anonymous. I hope you know that. I can't tell who answers what, and it is useful information, and I would appreciate you taking some time. I think there's about 30 questions on that. I think it's 29, but it's pretty bubbled, and some are comments, so you can type in some comments at the end. But teacher course evaluations are important, and actually I think they do impact me in terms of how I am evaluated. So I do take your comments, and other people take those comments literally. So I would value that feedback. And this is a controls class, so you know I like feedback. Homeworks 9 and 10 are, as I said, now available and due a week from today. They shouldn't be too effortful, I hope, and 10 I'm thinking might be sort of as an extra credit. I haven't yet decided, but maybe the material will be on the final, but you could have a week to play with that material before if you don't have time to turn in that particular homework assignment. The final exam is a couple of weeks from yesterday. It's on Tuesday, the 11th at 10:30 a.m. to 12:30 p.m. Today what I want to do is review and provide an overview really of why how we're doing controller design using Bode plots, and then we will get into the procedural steps for designing the second of these controller designs, which is the phase lead controller design, and we'll try to get into an example, and I have many things set up. Hopefully everything will go according to plan. Relative to designing controllers with the Bode plot, if you contrast it with the way we did controller design in Root Locus was really focused on where are these triangles, where are our closed loop poles, what's our transient behavior going to look like. That was Root Locus design. Bode plot design sort of looks at it the other way. And going back to Root Locus, we just sort of assumed that our steady state accuracy would be okay once we placed those triangles where we thought we wanted them in the appropriate location. Bode plot controller design really sort of flips the priority or the emphasis of those design considerations. In the Bode plot controller design, the main emphasis typically is how are we going to do when we stabilize the system with our steady state accuracy. So the first goal typically is how big or small, how do I adjust my gain to achieve the appropriate steady state error specification. That's the usual main goal of Bode plot. So how do you pick your K? The secondary goal is the transient behavior, and that's connected to the phase margin in a way that relates the phase margin with what we've looked at in the root locus strategy with respect to our percent overshoot or our angle or our zeta value. But the transient is how do we shape or how do we place the poles and zeros? Where do we put them and how far apart are they in this controller? Here's the rule of thumb that connects percent overshoot or zeta damping ratio with phase margin. If you're trying to, if somebody gives you specifications and you're wanting to design a controller based on a Bode Plot procedure and they give you a zeta specification, then you're going, well, how do I translate that into a phase margin? The relationship is given in equation 58, and it's just a rule of thumb. Realize that this is just a rough way of connecting zeta and phase margin in degrees, and that is that the phase margin is equal to 100 times zeta. As an example, if somebody said, oh, I want a zeta value of 0.7, and that one you should be locked in on in terms of the S-plane. That's now a 45-degree angle. That, if we had a pure two-pole system, that's why these are rule of thumbs. If we had a two-pole system and only poles, a pure two-pole system, zeta of 0.7 would correspond to a 5% overshoot. Well, if you wanted to achieve that, then you would say, oh, in my Bode Plot design, let me design for a phase margin of 70 degrees. That's the connection between zeta of 0.7 and phase margin. So if you wanted a small overshoot, a 5% overshoot, you might target a phase margin around 70 degrees. That's the connection. And in one of the homework problems, it might give you a zeta value, and you're going, well, how do I'm doing a Bode Plot design. How do I do this? I don't have a phase margin. Well, here's how you can now make that connection. If you're given a zeta and you're doing a Bode Plot based controller design, go ahead and just use this rule of thumb and say, okay, just to give me some way to start, let me scale that zeta by 100, and that's going to be my phase margin. If you had a zeta of 0.4 specified, then you would say, oh, I need a phase margin of 40 degrees, and that phase margin is in degrees. We are really focusing on two different types of controllers in this class with respect to Bode Plot design. If one can slow down the system response, what kind of a controller? Here is fill in the blank. So now this is an active lecture. Need to get up? No, you really just have to tell me lag or lead. Which one is it if you're okay with slowing down the system? Or what does that really mean? If I'm okay with slowing down the system, if you're looking at a Bode Plot, what does that correspond to? Slowing the system down. Do you adjust the phase to slow the system down? How do you slow the system down? Back off on the gain, right? If you reduce the gain, now that shrinks or causes the gain crossover frequency. Where the magnitude curve crosses 0 dB, that now shifts to lower frequencies. How do we do that with a phase lead or a phase lag controller? That's the implication here with this double-headed arrow or this double-lined arrow. What controller type? We have two. So now flip of a coin. Phase lead or phase lag? Up or down? I guess people are wanting to play, so let's go ahead and play. Let's say phase lag is up with your thumb and phase lead is down with your thumb. Is that clear? So now at the count of 3, I want to see thumb. So you can go in front of a mirror if you're at home playing along or listening, and decide which way you're going to place your thumb, up or down. What did I say? Lag was up and lead was down. So phase what? 1, 2, 3. Show me your thumbs. All right, we're all there. You acting like you're asleep, but you all know that this now is a lag controller. Maybe you're just wanting me to go slow this morning. That's fine. But that means, really, if you translate that into the S-plane picture, you have a pole that occurs at a lower frequency, which corresponds to being closer to the origin. But in a phase lag controller, both the pole and the origin are not separated by very, well, they are separated. You want them to be separated. That gives you the change in gain that you want. But both of those are occurring near the origin. Meaning if you had a pole at 0.01 and a 0 at 0.1, those are close to the origin, but their difference is a factor of 10 in terms of the ratio of the distances away from each other, and that's what you're playing with. So now you can throw your coin away, maybe. Now I have a different question, I think. If one does not want to slow down the system, then if lag was used to slow the system down, this one I think you know is the opposite, phase lead. And in the picture, the 0 now is closer to the origin, and these are, relatively speaking, further away from the imaginary axis, and the pole can be quite a ways away from the 0 in the phase lead controller design. In the phase lag, then, we're willing to move this crossover frequency, omega sub g, to a lower frequency or slow the system down, and here is what it might look like based on what we designed last time. The light blue curves are the uncompensated, and here I tried to hand sketch so that it emphasizes what we were doing with our phase lag controller. How do we design the phase lag controller? Do you remember? How do we generate the blue curves? B-O-D-E. You just type Bode into MATLAB, right? And you can do that on your homework. You can draw the Bode plot with MATLAB and then hand sketch on top of that if you want. So now you've sketched the blue curves. You need the gain, obviously, so you pick the gain to satisfy your steady state air spec. Then you sketch the blue curves, and you could hand sketch those. Now what's our next step? If we can slow the system down, what can we now do? And the picture is telling us really what we've done. We're backing off on the gain. We're lowering the magnitude curve. That red curve looks, I hope, lower than the blue curve in the top plot. But the way that we determine how much to lower that gain curve is based on the phase curve. We start walking back left to lower frequencies until we find a value on that blue curve that gives us the phase margin that we desire. And that phase margin typically needs to incorporate a little safety factor or a safety margin. In this case, I just walked back until I found a grid line that looked convenient to draw. So I walked back to 3 in terms of frequency and said, okay, here's the phase margin that I want. Now what do I do? If I now have my phase margin determined, I've now identified the new gain crossover frequency, omega sub c prime. Now what do I do? I've picked my gain. I haven't done anything yet with poles and zeros, have I? But in order to get this to drop, I need my pole to happen first and then my 0, but I want all of that phase messing around to be finished basically by the time I get to omega sub c prime. In order for that to happen, I need to locate my 0 a decade before omega sub c prime. I now know what z is, where my 0 is. It's omega sub c prime divided by 10. Then I say, okay, how much do I need to drop my attenuation? Or here is now the attenuation needed, and that now will give us our alpha value. That's the pole zero separation. That's how we design this phase lag controller. What happens with phase lead? Well, we don't want to decrease the gain crossover frequency. So now we're okay, and in fact we will allow that gain crossover frequency, which I'm now labeling differently so that we can maybe distinguish between when you're designing a phase lead and a phase lag. The new gain crossover frequency in a lag is omega sub c prime. In a phase lead, I'm just going to call it omega sub m for the new magnitude frequency. So if on the final you start mixing up omega c prime and omega m, it might confuse the grader, which is me. But if you do it right, it doesn't really matter. But here, one way to maybe keep the designs straight in your own head is to say, well, let me just use omega sub m for phase lead. What are we doing now? Well, now we actually look at the phase margin based on the blue curves. And in this particular case, we have a phase margin of 0. We want to now maybe achieve a much bigger phase margin. In this case, I'm achieving a phase margin of about 45 degrees or more. So now I say, oh, I have 0. I want 45 degrees. I now say, how much phase do I need to add? So I say, what I desire is 45. I have 0. So 45 minus 0 says 45. And let me put in a safety factor, because what happens to the gain curve? It actually goes to a higher frequency, which moves us to higher frequencies in the phase curve, which falls off or eliminates some of our phase margin that we might want or get. So we put in a little bit of a safety factor, maybe 5 degrees. So now we say, okay, my phase that I want to add is so much, let's say 50 degrees. I base all of my formulas now on that, and that's what we want to talk about, is what's the strategy or procedure for moving these curves from what they were, blue, to the red. But do you see that now we are really wanting our phase to be producing changes in the region that we're interested in or near our gain crossover? Now that phase is really bumped up, hopefully, if we can add that much, near our gain crossover. And we have not moved the crossover frequency to a lower frequency. It's actually now staggered or shifted to the right. And what's the relationship between our zeros and poles in the controller? Now the 0 begins first, and the pole begins later in terms of frequency. That's now the phase lead controller. So this is helpful, or this phase lead technique is useful when the phase margin needs to be increased. In our case, in this example, from 0 degrees up to something else, 45 degrees, without lowering the gain crossover frequency. We're not wanting to slow down the system. So here's the procedure. Now we can start maybe taking notes, because I was maybe going a little bit quick in terms of scrolling for note taking before. But here, in the first step, it's just like in the phase lag. We need to determine the gain to satisfy our steady state air spec. Step 1 is then determine the gain constant needed to satisfy the steady state error criterion or specification. And again, I've provided an extra video and notes for talking about what in the world is he doing by adjusting that gain K. And it's not a very long video or set of notes. Now we simply draw the Bode plot. We now plot the uncompensated, although this requires the gain from step 1, Bode plot using the gain determined in step 1. Those are identical steps to the phase lag. Now what you do is you determine whether or not the phase margin that now exists is acceptable. Determine the phase margin. And you need to be able to find that from a given Bode plot sketch on the final. You need to be able to find the gain margin and the phase margin. Determine the phase margin for the uncompensated system, and let's go ahead and call that PM sub U. In our particular illustrative example that we were talking about earlier, PM sub U was actually 0. But typically that might be 20 degrees or 10 degrees or something. It could be a negative. That means you just have to add more phase. If this is sufficient, if PM, phase margin uncompensated, is sufficient, you know what to do there. Pull out your cell phone, social media, take a break, you're done, right? It's finished. This particular system, wow, all I had to do was set the gain and magic. The phase margin actually was enough. So if the phase margin is sufficient, no phase lead, controller is needed. However, if it's not sufficient, which if I design the problem properly on the final, you'll fall into this category probably. If not sufficient, determine the necessary amount of phase that you need to add. Determine the necessary amount of phase needed to satisfy the phase margin spec. And this is now much different than what we did in the phase lag. Here we actually say, oh, what is the phase that I need? That's what I'm calling phi sub m. Well, that's going to be the phase margin desired, maybe somebody wants 70 degrees, minus the uncompensated phase margin, which maybe is 20, plus this safety factor, or phi sub Sm. Phi sub Sm is a safety margin in the same units that you're using for phi sub m, which is typically degrees. which is needed to account for the shift of omega sub g to a higher frequency. And typically you can just assume that phi sub m, phi sub sm is 5 degrees or 10 degrees. Really depends on how fast your phase curve is moving near your new gain crossover frequency. Now we've figured out how much phase to add. In order to add that much phase, that's going to depend on how far the pole and the zero are apart, the pole-zero separation. When did we kick the zero in or start it, and when do we kick the pole in? Step 4 then is concerned with calculating that separation. Calculate the pole-zero separation which will supply the additional phi sub m that's needed. And that pole-zero separation, again, we're going to go ahead and call it alpha in the phase lead design, but it's now 1 plus sine of phi sub m. Remember, you've calculated phi sub m in the previous step, so you can take the sine of that and divide by 1 minus sine of phi sub m, and that now tells us how big or large this pole-zero separation is. And you can now refer to equations, or one equation, 10, 11, or you can look at you can look at figure 10.4 to see how alpha and phi sub m are related. You can't add a really large phi sub m. If you look at that curve, phi sub m in an extreme is, let's say, 60 degrees, maybe. That's pretty big for trying to add that much phase. If you needed more phase, well, now maybe you just add in 2 of these first order pieces, and now you have 40 degrees from one and 40 degrees from another. Now you've added 80 degrees total. Hopefully in this class you'll only need to add 1 first order controller to produce the phase lead that you want. Now we simply need to figure out where do we put these poles and zeros. We now know how far they are apart, but we need to pick one so that we know where to locate them. On the Bode plot, in step 5, we now need to go back to the blue line on the Bode plot and identify the frequency that's basically halfway between the pole and the zero. So on the Bode plot, find, or I should say that corresponds to the magnitude that's created halfway between those two in terms of shift. Find the frequency at which the uncompensated gain curve is actually equal to minus 10 log of alpha, and that's base 10 log. You've just found alpha in step 4. You now take the log of that, base 10, and scale it by minus 10. You go over to your magnitude plot and you say, oh, where am I? I guess I can sort of show that. What color do I want to say? Let's say that now well, obviously here, that particular point was minus 10 log of alpha. So we find where that is on our blue curve, and we say, oh, there is our frequency that we're going to have our new gain crossover occurring at. That will now be our omega sub m frequency. So designate this frequency, which we're now calling omega sub m, the new gain crossover frequency. Now we go through the equations and we actually see, well, we found the separation and we found omega sub m, and omega sub m is really related to the pole and zero location. Now we can calculate the pole and zero location from the data that we just have collected. So calculate the pole and zero locations by calculating the time constant. And tau is now 1 over omega sub m times the square root of alpha. So now we have a time constant and we have their separation. We now have enough to write down, and now look at how we're doing this. This is now different. We've now flipped really sort of the way that we think of the pole and zero relative to this alpha, or separation between those. This is now, the zero has a time constant of alpha tau, and the pole has a time constant of tau. And this is our phase lead controller. And that's just the opposite of how we related alpha and tau in the phase lag. Let's now look at an example to maybe put this into something a little bit more concrete. Suppose that somebody gives us a plant that's K S S plus 2. And if you want to just sort of center yourself as far as what you're doing, okay, they've given us G. Now I need to find K, and then I can sketch the Bode plot for this, and then start doing the design of G sub C. Well, in order to figure out how to adjust G, and what could G correspond to? What physical piece of equipment, or what kind of a system might this G of S correspond to? We don't have a lot of these floating around. Well, we might in the ECE building, but you don't have a class in motors. This is a DC motor. Could be. You could think of this as a DC motor. So now you have a DC motor you're trying to control. Suppose now the design specs are as follows. Suppose that somebody says, well, I want the steady state. Oh, I could, just for grins, pull out a system from a bag, a G, a transfer function, and hand it to the class, and I could go around to each of you and say, give me something interesting or tell me something interesting about this system. In this case, what do you know about that system just by looking at it? It's a type 1. Wow, somebody's reading my mind. Type 1. What's a type 1? We have a pole at the origin. What good is a type 1 system? It gives us zero steady state error due to constant reference input. So if I now can stabilize this system, and could you draw the Bode plot for, the root locus for that? That's an easy one, isn't it? They come together and separate. We have the branches going off at plus and minus 90 degrees, and where are they meeting in the root locus? Where are the branches meeting? Halfway between at -1. So you now know the settling time. You crank up the gain a lot, are you going to change the settling time? You're stuck at -1, aren't you? So you're not changing the settling time by increasing the gain K. What could you do, or what will you do if you just continue to increase the gain K? What kind of a step response behavior will you obtain if you keep cranking up K? Your percent overshoot's going to start getting bigger and bigger, isn't it? And you may not like that. But your system will get faster in terms of how quick it gets to where it's going for the peak, but it'll just still take the same amount of time to settle. So your settling time is the same. It gets there quick, but boy, does it get a far away from where you wanted. Maybe, if K is big. But you see all of this now, right? Just by looking at G. Now we want to change that, and we say, what if I gave you on the final, maybe I haven't slept for a while or had a bad, maybe a good day, depending on your perspective. What if I said the steady state error due to a constant needs to be less than 0.1? You go, yes, he messed up. All I have to do is find a K to stabilize the system. I don't have to add a pole or a 0, do I? Because this is a type 1 system. If I say, give me a steady state error less than 0.1, you know it's going to be 0 since it's a type 1. Is that clear? So now I've had my coffee, which I don't drink, but so I'd probably have a really bad day if I started designing exams after coffee. Nothing against coffee. I just never acquired a taste. So sorry, Starbucks. Anyway, where were we? Now I have the steady state error spec due to a unit ramp. Now I will have a constant or a non-zero value for steady state error. And suppose that I say, let's let that less than or equal to 0.05. And let's give us another design spec. Let's say that the phase margin needs to be bigger than 40 degrees. And so far with 1 and 2, you could design either a phase lead or a phase lag, right? I haven't said anything about the speed of the response. So in my third design constraint, I'm going to force you to design a phase lead by saying do not slow the system down. All right, final exam time. Now what do we do? We've been given a plant. It's type 1. You go, oh, well, I do have to worry about the gain because now I do have a non-zero steady state error, or I do have accuracy concerns with a unit ramp. Now I'm essentially in an earlier problem. Now maybe I'm a robot trying to weld or solder on this ramp. If I'm assembling cars or something and I've now made my robot go up to a ramp. Now I'm wanting to track the reference ramp fairly tightly. I want the error to be 0.05. Now what? I have to find a K, do I not? So the first thing that I need to do is figure out what's K before I can even sketch the Bode plot. I could sketch a Bode plot for a generic K and what? Oh, shoot, I messed up. Well, don't erase anything. Keep the phase curve exactly as you've drawn it. Now just adjust the entire magnitude curve up or down depending on what you determine your gain now needs to be. So now you say, oh, my K needed to be 10. Well, now you take 20 log of 10. You just adjust your gain curve everywhere up 20 dB from where it was. Okay, well, let's avoid that and let's find K to begin with. So let's find K using the steady state error specs. And we know the steady state error is 1 over the velocity gain constant, 1 over K sub V. And now I need to have a commercial. You can now see lecture 9.1e if this isn't making sense. And that's now available to you, but really that shouldn't be too foreign to you. I think you've played with these error constants in earlier homeworks. How do we find K sub V? Do you remember? Well, you have a couple of weeks to figure this one out, right? It's the limit as s goes to 0 of s g of s. And that may already be on your crib sheet. So now if we let the s go to 0, we now have this is k over 2. That's K sub V. But we needed our steady state error, which is now 1 over K sub V, which is 1 over in terms of the K that we have identified in our plant G of S. K sub V is K over 2. This is now 2 over K, and we wanted that to be less than or equal to 0.05. A lot of people are forgetting their calculator, so that's now 5 over 100. I wouldn't recommend that on the final, just a hint. But now you have 2. Now we just solve for K. So now we have 2 times, we'll multiply both sides by 100, multiply both sides by K, and divide both sides by 5. And we want that to be less than or equal to K. Or the final may not be this convenient for hand calculations. That's why I'm suggesting to bring a calculator. K now is bigger than 40. Well, let's not get too hung up on bigger than. Let's just let it be equal to 40. So now we have K equal to 40 in our system. And we have G of S specified. This is now in pole 0 form. And if we wanted to sketch that in a Bode plot by hand, we would want to put that in time constant form. We only have to worry about one of these linear factors scaling it or making the constant equal to 1. And now maybe you can visualize the Bode plot based on that time constant form of the transfer function. hopefully somewhere before class I did that. I went ahead and in MATLAB said, okay, let me create a transfer function, TF. It had a numerator of 40 and it had a denominator of s times s plus 2. And so now I have an s squared plus 2s plus 0, and that's now my denominator polynomial. G looks like 40 over s squared plus 2s. I sketch the Bode plot and put some grid lines on it, and there is now my Bode plot for this DC motor with a gain K of 40. And you can probably see what's our phase margin. Do we have is this system stable? Could you have answered that without even looking at the Bode plot? I give you a gain K of 40. For this G, what did you just tell me about the root locus? It's always stable, isn't it? No matter what K is. So we knew that this was going to be a stable system. Just how big K is depends on sort of what our overshoot is, or that's going to reduce our phase margin in this curve. But if we go back here into something that I can mark on, I now can maybe see that my gain is crossing at about there. So that is now 2, 3, 4, 5, 6. And that's now where I would determine my, what's that quantity called? That's my phase margin, and we've been calling that now phase margin uncompensated. So whatever that is, we now have it available, and now what do? We need to go back to our design specs and say, oh, is that 40 degrees or not? It's not, is it? If it was 45 degrees, it would be at minus 135. So we're quite a ways away from 40 degrees. But let's say that we are now at maybe 20 degrees to be generous for our PM sub U. Is that true? Or 15 degrees. Now, what are we wanting to do now? What step are we in this process? Do you remember the recipe? We need to find the necessary phase that we need to add to our system. And we wanted 40 degrees. This was our phase margin desired. Wow. Maybe I will start drinking coffee. This is now whatever we said it was, phase margin uncompensated. And this is our safety margin, which we could say is, let's say, 10 degrees. So now what do we know? We now know the phase that we want to add. We need to add 30 degrees with our controller. What's our next step in this process? So now we found this. Step 4 says calculate the pole zero separation. And this is why you might want your calculator. Thankfully, I did bring my calculator because I don't have a clue what I'm doing now until I find alpha, right? So now I need to find the sine of What was that value that I had created for phi sub m? 30 degrees. So now I need to go and say, okay, I found phi sub m to be 30 degrees. Alpha is now 1 plus sine of 30 over 1 minus sine of 30. And if I could calculate that, oh, you guys remember sine of 30? Duh. Oh well, like I said, I didn't have my coffee. So now I have 3 halves divided by a half. Or I have a separation of 3. Now what do I do? And I'll have to follow up with this after class. It looks like we're out of time, unfortunately. I know you were all enjoying this. But now I need to find my omega sub m, and then I'm basically done. So I'll put that all together, hopefully, in AC after class notes that you can then reference for your phase lead controller design.